Yeah.
Hello everyone, I am Hugo Talibart. I'm currently a postdoc at the National Museum of Natural History in Paris. And I'm going to give you an overview of the work I recently published with my PhD supervisor, François Coste at INRIA Rennes. The motivation behind our work is the sequence annotation problem. Thanks to sequencing technologies, there's an increasing number of protein sequences available. And the problem is how to predict the structures and the functions of all these sequences. In vivo and in vitro annotation methods cannot keep up, and this calls for in silico annotation methods. The main approaches to annotate a protein sequence is to transfer annotation from identified homologs. And the most straightforward way to identify an homology between two proteins is to align a carry sequence to an already annotated target sequence, typically using BLAST, which will provide a score which we can then use to predict the homology between the two proteins and transfer annotations. To predict a more remote homology, a successful approach is to, instead of relying on a single sequence, to capture the conservation and allowed variability in whole sets of homologous protein sequences. A target family can be modeled by a profile hidden Markov model, which is a probabilistic model which provides match states, which gives the probabilities to find each amino acid at each positions. And between these match states, there are insertion and deletion states. A carry sequence can be aligned to a profile hidden Markov model using Hammer, which will provide a score, which we can then use to predict the homology. And to predict an even more remote homology, we can take it further by enriching the carry sequence as well with close homologs and perform pairwise profile hidden Markov model alignments using HH-align. This allows for a more sensitive remote homology detection. While these methods are powerful, they rely on the simplifying assumption that positions in a protein are independent from each other. But in reality, proteins fall into a three-dimensional structure, which implies that there might be dependencies between residues that are distant in the sequence, for instance, because these residues are in contact. And the fact that these residues are in contact will constrain the evolution of the amino acid at two positions. And in the multiple sequence alignments, positions will be correlated. And we were wondering whether taking these distant dependencies into account could assist sequence alignments and improve homology detection. And these dependencies cannot be modeled by profile hidden Markov models since they model each position independently. So instead, we decided to rely on a different model, the POT model, which you probably know for its success in contact prediction. As introduced by direct coupling analysis, a POT model represents a multiple sequence alignment of protein sequences. Typically, it would be an alignment of a sequence of interest and its close homologs. And it defines a probability distribution which looks like this. So it is a normalization constant times the exponential of a sum of parameters evaluated at the different letters of the sequence. Both models have two types of parameters, the field parameters and the coupling parameters. The field parameters are vectors. There is one vector vi per position in the multiple sequence alignment. And this vector gives the propensity for each letter to be at each position. So in addition to these parameters which describe positional conservation, there are also the pairwise coupling parameters, which we denote Wij, which are interaction matrices between two positions I and j in the multiple sequence alignments. And roughly speaking, they capture the direct correlation or anti-correlations between letters at two positions in the alignment. So initially, POT models were introduced to predict coevolution between residues, since it was shown that the norms of these pairwise coupling parameters were shown to be great indicators of a direct interaction strength between positions. And this led to a breakthrough in the field of contact prediction. We propose to look beyond just the coupling norm and to see POT models as an extension of profiles where field vectors would be like match states And there are also these pairwise distant dependencies that can be modeled with the couplings. And we are wondering what would be the performances of POTS models in alignment-based homology detection. So as a first step in this direction, we design a pairwise POTS model alignment methods, PPalign. PPalign compares two protein sequences by aligning POTS models representing them. To put it simple, we define the best alignment of two POTS models as an assignment of mappings of positions between the two models so that they are one-to-one and non-crossing, and they maximize a scoring function, which is a similarity score between the two models, which we based on the scalar products between the parameters. Unlike profile-hidden Markov models, POTS models have non-local dependencies, which make their alignment a problem likely to be NP-hard. So to tackle this difficulty, we made use of existing work on structural alignments to formulate this problem as an integer linear programming problem, which can then be solved by an existing efficient solver. To provide reliable homology detection prediction, we need to be able to provide reliable alignments. So this was the subject of our publication in BMC Bioinformatics, where we focused on the quality of our alignments. We built a benchmark of reference pairwise sequence alignments, which we built from structural alignments with low pairwise sequence identity. And we compare our alignments with the reference alignments. And I will briefly sum up our results. So first of all, despite the fact that this problem is likely to be NP-hard, we were able to obtain a solution in tractable time with 1 minute and 37 seconds on average. In terms of alignment quality, we had slightly better F1 scores than our main competitor HHAlign, which performed pairwise alignments of profile-hidden Markov models built on the same data. And our performances were especially better when the sequence identity was the lowest. We showed that direct coupling information could improve alignment quality. It was particularly significant in 3 cases out of 22. However, there are still some cases where the alignment was worse when taking into account this direct coupling score. And we are working on improving these results by trying to infer POTS models more suited for pairwise comparison, which is a different challenge from contact prediction. So to sum up, PPalign compares protein sequences by aligning POTS models representing them. In tractable time, we showed encouraging results in terms of alignment quality, which suggests that direct coupling information could improve protein sequence alignments and therefore might improve alignment-based homology search. I want to thank my collaborators, François Coste and Mathilde Carpentier. I want to thank the organizers for providing me the opportunity to present our work. And finally, I want to thank all of you for your attention. And if you're interested, you can come see my poster or you can contact me at this email address. Thank you.
Are there any questions?
Can you hear me?
Yes, I can hear you.
Oh, I think it's a very nice idea. You're now competing with a world in which much more accurate structures can be computed. Have you tried comparing how your method works with running something like an AlphaFold method and directly aligning from those?
No, we haven't tried that yet. When we proposed our method, AlphaFold, I think wasn't released yet, and we didn't have time to compare the results. But it would be a good idea to see to compare them.
Yeah, I don't think that's what you've done. I think is still a very nice and neat piece of work, so it shouldn't be put off by the AlphaFold stuff.
I'm sorry, I couldn't hear what you said.
Independent of the AlphaFold advances, I think what you've done was a very nice and neat piece of work.
Sorry, I'm really sorry. I cannot hear. Could you speak close?
Compliment.
Okay, thank you. It's nice. I just I don't know what you said, but thank you.
In spite of AlphaFold, your work stands on its own. Very good.
Okay, thank you.
So there's a question online by Chengzhen Zhang. Is it possible to align a parse model to a contact map?
That would be a different problem, but I think it's possible if we see the alignment, if we see the contact map as a kind of POTS model where the parameters would be 1 if there's a contact and 0 if it's not a contact, but I don't know how it would work in practice. I mean, it would change a lot on the similarity function that we would use. I think it's possible. It's a different problem, I think.
Okay. One last question.
Hi, can you hear me?
Yes.
Great talk, thank you. I'm just wondering if you calculated your POTS model using your own program, or if you use something like CCMP.
Sorry, if I tried to?
Did you use CCMP to calculate your POTS model, or did you use your own?
Oh, yes. In this paper, we used CCMP, but currently we are working on our own inference method, which would be inspired by MFTCA. But yes, in this paper, we use CCMP to build the POTS models. CCMP Pi, actually.